let's look at some of the details of heat transfer, heat transports in the ocean. So let's say we have a latitude where the heat divergence is zero. So there is no heat going out, there is no heat coming in. So the heat transport at that latitude is zero. You have net heat flux coming into the ocean, which in this book's convention is negative. And then you're trying to figure out heat transport across another latitude phi, which is what we had written equations for in the previous podcast, 1112, equation 1112. So the heat net heat flux coming in has to equal the heat getting out of the box here, right? So if this is a heat loss, then heat has to come in to compensate for that. Or if it's a heat gain, heat has to go out for equilibrium to be maintained. You do that with the atmosphere in each ocean, and you see again the total transport needed for maintaining the equator to pole temperature gradients in the modern climate, let's say, given the distribution of radiation at the top of the atmosphere. We looked at the energy excess and energy deficit, and we calculating this heat flux divergence out of the low latitudes. And we had said ocean does the work at low latitudes, and once you go beyond the mid latitudes, the ocean is not transporting any northward heat transport. It's all the atmosphere and the eddy transports that are doing all the work. Obviously, ocean is very heavy, but the currents are really tiny compared to the atmospheric wind speeds in tens of meters per second, as opposed to order meter per second or centimeter per second in the ocean. Ocean is deep, but the atmosphere is light and also has temperature contrasts up into 10 kilometers or so, whereas the ocean is 3 to 5 or 6 kilometers. Okay, so we can then look at the northward heat transport by each ocean. Because they have boundaries, we have to consider each ocean separately. And immediately you see the contrast here. The North Atlantic is doing a net northward heat transport. So you're going from south to north across the equator. So there is a strong northward heat transport by the Atlantic Ocean. Basically, the sinking water is being compensated by this cross-equatorial transport, which we saw in the salinity transects and the water mass identities, right? The Indian Ocean does not exist to the north of about 25 north, 20 north or so. So its heat transport is southward at all its latitudes, because it's getting in the deep and intermediate waters, and it's taking out water to the south. Warm waters are going south and cold waters are coming north, so there is a net southward heat transport. The relative temperature profiles matter a lot as well, right? Whereas the Pacific Ocean is diverging heat towards the poles from the low latitudes in both hemispheres, with some asymmetry because of the connection to the Southern Ocean. Okay, so this is something that's easy to understand. Just to put it again in the context of the atmospheric heat transport, this is the total flux in the atmosphere. Again, there is a strong asymmetry. And we can convert it into mean meridional circulation, so the Hadley cell, Ferrel, and polar cells. And you can see there is a, this is only going from 10 south to the north. And you can see that the mean meridional circulation is doing northward heat transport, and there is actually a southward heat transport beyond the subtropical gyre because of the Ferrel cell, the indirect cell, and so on. And then the eddies do the northward transport. The mean meridional circulation does a small northward transport here. So the direct meridional cell transportation is actually not poleward, beyond the subtropics, it's actually towards low latitudes. Okay, that's kind of unique. And the eddies can be split into transient eddies and stationary eddies. So there are features that are attached to some downstream of the mountains in the westerlies, at the edge of the continents, over the ocean, and so on. So these are semi-permanent features. They have seasonal variability, but the seasonal transient eddies, the baroclinic instability shedding strong time varying eddies are shown here. And you can see that the total eddy transport and the transient eddy transport is almost equal. So the so-called permanent eddies do a little bit of excess transport here, but in the lower latitudes, mostly the transient eddies. So even where the mean meridional circulation can do a lot of the transport, eddies actually contribute as soon as the Hadley cell terminates and its transport becomes negligible. Okay, so quite a stark contrast to the ocean. We have to interpret the sea surface temperatures in this context. You have lots of excess energy here, creating these warm temperatures with Ekman divergence and upwelling, or where the ocean is soaking up heat. And then you have high latitudes where the Kuroshio and the Gulf Stream and the other Brazil Malvinas and East Australian current bring tropical heat down and are lost to the atmosphere. So the higher latitudes, as we saw, have lots of heat loss, especially in these regions where you have strong continental air coming off. So these have to be interpreted in terms of the mixed layer heat budget, so the vertical and horizontal advection processes, as well as the surface heat exchanges, which can be combined with these strong surface current components. This we had seen in the 10th chapter. There is the strong V component, meridional component, and this is a strong zonal component. And obviously the Gulf Stream is obvious in both the meridional and zonal component. Here you can see that the zonal component is westward, and here it's eastward, so the signs change, but the meridional currents are northward everywhere. And there is lots of eddies once you go off once the Gulf Stream separates and becomes the North Atlantic current and the Norwegian current and so on. And lots of eddies here as well in the meridional component. Remember that in general, the meridional velocities are not as strong as the zonal currents, because Coriolis and the trade winds and everything is mostly zonal, because the Coriolis varies with latitude and puts a strong constraint on crossing the latitude lines, because you have to change your vorticity and so on and so forth. Okay. In the western boundary currents, obviously you can get strong meridional currents as opposed to the interior, where you can see very weak currents in general. Okay, so this is the estimates that are done based on data. There's various methodologies to do this called inverse modeling, for example, where you take data that exists and you take the surface heat fluxes and then you constrain the transports needed. So this is split into shallow transports, deep transports, and bottom transports. So you can see that there is shallow northward transport all across the Atlantic, which corresponds to the northward transport, predominantly northward transport by the ocean. There are small amounts of southward transport in the deep and bottom columns of the ocean. So there is a net escape of 23, which has to be balanced by what is sinking. So 15 plus what is going across has to balance what is coming out. Similarly, for the Indian Ocean, except that the Indian Ocean has to convert the bottom and intermediate waters back to the surface and take it out to the north because it's blocked off to take it out to the south because it's blocked off in the north. And there is some heat coming in from the Pacific Ocean into the Indian Ocean through the Indonesian through flow, which is part of the upper branch of the meridional overturning. Okay, so here is sinking, western boundary transport, mixing with the Ross Sea with LC transports, and converting to surface, circulating the Southern Ocean, and then getting back through the Indonesian seas around Africa back to the sinking regions. Okay, so the Southern Ocean, obviously a channel, has massive amounts of heat transport, right? Not much of divergence, but it's circulating. So it becomes critical to figure out what is the time scales with which the heat can get exchanged. Okay, so this is basically circulation patterns in sphere groups. So make sure that I'm just talking about transports and not really heat transports, okay, mass transports and not heat transports. Nonetheless, that gives you a sense of which way the heat is being transported by the warm waters and by the cold waters. So the difference, so here you have warm waters going north, cold waters coming south, so you have a very strong northward heat transport here. Okay, that's intuitive sense you have to have of how to interpret these inverse calculations made constrained by data.